Alright, in this video we're going to look at the marriage problem. The marriage problem considers a sequence of objects, specifically n of them. Each object is assigned an arbitrary value, which we will represent as integers. The goal of the algorithm is to output the index of the maximum valued element. The maximum valued element in the sequence, which we will call n sub n. Now this problem could be perfectly solved in linear time, but for the following constraint. As the algorithm encounters the objects, it must make its reject and accept decision permanently the first time it encounters the object. Therefore, a linear algorithm in which we consider all n elements and then go back and output the index value of the maximum valued element is not legal, because we must accept the element as we encounter it. This makes the problem, in fact, impossible, because the only way to be certain that we have selected the maximum valued element is to consider all n elements. And therefore, once we've considered the first n-1 elements, our only option is to output the last element. The probability that the last element is the maximum valued element is only 1 over n. So therefore, the algorithm that considers all the elements in sequence has a probability of success only 1 over n. This is equivalent to the probability of picking any arbitrary index in the sequence. So the question is there an algorithm that has a better performance than 1 over n? We will prove that the following algorithm has probability of success greater than 1 over n. The algorithm has two phases. In the first phase, we reject the first k elements, keeping track of m sub k, which is the highest valued object in the first k objects. In the second phase, we select an object. We select the very first object whose value is greater than m sub k. So the index value that the algorithm outputs we'll call s. And so what we're going to prove is that the probability that s equals I, remember I is the location of m sub n, is strictly greater than 1 over n. So we want to find an expression for the probability that s equals I. This is the probability that our algorithm succeeds. The way we're going to do this is to break that expression up into an average of conditional probabilities So the idea is that I can be anywhere from 1, the first element, to n. And so we're going to look at the probability that we succeed given I is at 1 all the way up to n. We're going to add all those probabilities together because they are mutually exclusive events. And we're going to take their average, and that will give us the probability, the total probability that the algorithm succeeds. So let's look at different cases of I to see why we're doing it this way. So let's say that I is less than or equal to k. So if we drew this diagrammatically, we would have our sequence of objects. This is the nth object. This is the first object. We'll call this the kth object. And so we're assuming I is somewhere in one of these 3 objects. Now, by the specification of the algorithm in phase 1, we unconditionally reject all 3 of these objects. Therefore, the probability that S equals I given I is less than or equal to k is 0. So let's look at the case. Let's look at one more special case, and then we'll consider the general case. So we're going to look at the special case where I is equal to k plus 1. So this considers the case where m sub n is this element. What's the probability that our algorithm selects S equals I equals k plus 1 when m sub n is the k plus first element? Again, by the specification of the algorithm, phase 2, we select the very first element whose value is greater than m sub k, and since by definition m sub n is greater than m sub k, we'll always select m sub n. So in this case, our probability of success given I equals k plus 1 is 1. So the last case we're going to look at, and is the most general case, is when I is greater than k plus 1. Okay, this is the case, this is the general case when I is greater than k plus 1. We want to know, again, what is the probability that S equals I, given given I is greater than k plus 1. Well, our algorithm will select I so long as none of the intervening elements here are greater than m sub k. So we're going to call the intervening elements the J set. We're going to call the first k elements the K set. And we're going to call the disjunction of the K set and the J set the R set. So the R set is all of the elements that we reject. Now the proposition that S equals I is logically equivalent to there does not exist an element E in the J set such that its value is greater than m sub k. Now this proposition is logically equivalent to m sub r, the greatest value in the R set, is contained in the K set. So if there is an element in the J set greater than m sub k, then S will not equal I because the algorithm will select that element E. So for S to equal I, it has to be the case that there does not exist an element in the J set whose value is greater than m sub k. So therefore, the greatest value in the R set is contained in the K set. In fact, the greatest value in the R set is identical to m sub k. It turns out the probability of this event, is very straightforward to answer. So the probability that the greatest element in the R set is contained in the K set is simply the probability that an arbitrary element from the R set, namely m sub r, is contained in a subset of R. So it will be the size of the two sets. And the size of the K set is K. And the size of the R set is I minus 1 because we're assuming that the R set is every element up to I. So we now have an expression for every one of these conditional probabilities. So therefore we now have an expression for the probability that our algorithm succeeds.